Hey guys, today we're going to take a look at section 4.4, Improving Triangles Are Congruent by SAS and HL. We're going to go ahead and take a look at some vocabulary terms here. So first of all, reviewing the leg of a right triangle. Remember that the legs are the two sides that are adjacent to the right angle. And just a reminder, so when we say adjacent, we mean that it's touching or next to. So when we take a look at a right triangle, this is our right angle. We're talking about these two sides being the legs since they are touching that right angle. Next term to define is hypotenuse, and that is the other side in the right triangle, so that's going to be the side that's opposite the right angle. And since it's opposite the right angle, of course, that means that it does not touch the right angle. So this over here is going to be our hypotenuse. And then the last term that you see here that we're going to define applies to all triangles, not just a right triangle, and that is the included angle. The included angle is the angle that is in between two adjacent sides. And like I said, that's going to be in any triangle. If we look specifically at the right triangle, our right angle here would be the included angle between our two legs. But again, we could have any triangle, and the included angle is the one that's between the two adjacent sides that we're referencing. Postulate 20, the side-angle-side congruence postulate, says that if two angles and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. So, it says if side, in this particular example, if side RS is congruent to side UV and angle R is congruent to angle U, and side RT is congruent to side UW. So we have the sides congruent, the included angle, and the other side that's adjacent to the original side. If those are all congruent, then we know that the triangles must be congruent. So again, with the side-angle-side congruence postulate, the order is important. So we have a side, an angle, and then a side that are congruent. We can't have a side, and an angle over here. That angle does have to be the included angle, which is basically formed by those two congruent adjacent sides. So let's go ahead and take a look at our first proof here using the SAS congruence postulate. We're given that GF is congruent to IF. We're also given that FH bisects angle GFI. We want to prove that the two triangles are congruent to each other. So first statement here we see is GF is congruent to IF and FH bisects angle GFI. And as you know, we're always going to start our proofs with a given, which that one is what we are given. Before we get further in this proof, let's just go ahead and take a look at our given and see kind of what that tells us in our diagram. Let's mark a couple things so we can kind of see our goal here and see how we're actually going to develop this proof. So we know that GF is congruent to IF, and we know that FH bisects angle GFI. So if HF bisects angle GFI, that's going to tell us that GFH and IFH have to be congruent. And that's because of what we know about angle bisectors. So that second statement there is that angle GFH is congruent to angle IFH. And that's simply just the definition of an angle bisector. If we know that that segment is bisecting the angle, we know that's going to form two congruent angles. So when we look at this, again, if we're using side, angle, side, we know, again, that order is really important. So we have a side, we have an angle, so we know that we're going to have to show that this side is congruent to the corresponding side in the other triangle. Well, when you look at this drawing, you're going to see that FH is the same side in both of our triangles. So we know that that's congruent to itself, and that is based on the reflexive property. So we have shown that we have corresponding sides congruent, an included angle, and another corresponding side congruent that's adjacent. So we see that side, angle, side congruence postulate in form here, so we know that the triangles must be congruent. And that is because of the side, angle, side congruence postulate. Next proof, given that ST is congruent to UR and that ST is parallel to RU, then we're going to try and prove that triangle SRT is congruent to triangle UTR. So let's go ahead and let's just start marking some things before we really get into our proof. This one's a little bit more difficult than the previous one. So we know that ST is congruent to UR, and we know that ST is parallel to RU. So we know those are parallel. And we're trying to prove that SRT is congruent to UTR. So when looking at this, let's go head over here to our proof, and we see our statement. So we see that ST is parallel to RU. Well, that is something that's just given to us. So let's go ahead and justify that as our given. You can see the next statement in our proof is saying that angle STR is congruent to angle URT. So we see that STR is congruent to URT. If we think about the justification for that, we see that these lines are parallel. So that would mean that RT would be the transversal. So we know that STR and URT are going to be alternate interior angles. So our justification for that would be alternate interior angle theorem. So we know that this is going to be congruent to this. So we see we have a side, we have an angle. So we want to take a look at this side and, before we go any further, I'm sorry, we have to use our other given, and that is that ST is congruent to UR. We hadn't used that yet, although we had talked about it. So now all we have to do is show that RT is congruent to itself, because that is a common side among those two triangles. So we're going to say that RT is congruent to RT, and that is because of our reflexive property. And then we can say that we have two corresponding sides being congruent, and the included angle in between them also being congruent, so that we know that the triangles SRT and UTR must be congruent. And that is again because of the side angle side congruence theorem. Let's go ahead and take a look at some more proofs. We're going to start involving some properties of shapes here. So we see in this diagram ABCD as a rectangle. We want to see what we can conclude about triangle ABC and triangle CDA. So we're looking ABC right here, and then CDA right here. So if we take a look, first thing that at least I see from this diagram is I see that both B and D are labeled as right angles. Now, we know that it's a rectangle, so we know that those would need to be right angles regardless of whether they are labeled or not. We're trying to see what we can conclude. So because our topic right now is side angle side and triangle congruence, we can assume that we're probably looking for something along those lines. So let's take a look here. When we have a rectangle, we see that these again are right angles, which we know. We know that AC is going to be congruent to AC, so that's something that maybe we would want to use here. We have to try to think about some other properties about rectangles. So another thing that we know about rectangles is that the opposite sides are both parallel and congruent to each other. So we know that AD is going to be congruent to BC. And we also know that AB is going to be congruent to DC. So when we label those, we can see that, in fact, we do now have enough information to be able to say that these two triangles would be congruent based on side angle side. So we can conclude that they are congruent. And we know that, and I'm just going to summarize kind of what we said, that opposite sides, sorry about my pen issues here, guys. So opposite sides of a rectangle are congruent. And that would combine with the fact that those do have to be right angles, we are able to say that by side angle side, that those two triangles are congruent. All right, take a look at the next diagram. Very complicated diagram, but let's go ahead and kind of dissect what's happening here. So in the diagram, we see that A, B, C, D, and E, F pass through the center M of the circle. So we have A, B, we have C, D, and we have E, F all passing through the center circle here, which is labeled as M. We are also given that angle 1 is congruent to angle 2, which is congruent to angle 3, which is also congruent to angle 4. So all four of these angles here are congruent. And really, we wouldn't even need to be given that because you can see, for instance, that 2 and 4 are both vertical angles, so they're congruent. We know that 1 and 3 are vertical angles, so they're congruent. So we could kind of make some of those assumptions ourselves based on the properties of vertical angles, but we are given that those are all congruent to each other. We're going to go ahead and try and prove that triangle DMY is congruent to triangle BMY. I'm just going to highlight those since this diagram is a little more complex, so we can see exactly what we're talking about. So we're talking about DMY, so this triangle here, and BMY, which is this triangle down here. All right, so let's go ahead, let's set up a two-column proof. Since it says prove, so we typically want to start a proof with a given. So let's go ahead and use something that we know that's going to be helpful to us. We were given that these angles were congruent, and we know that 3 and 4 are both one of the angles in our triangle. So let's go ahead and use the fact that angle 3 is congruent to angle 4, and that is because it was given to us. We then want to go ahead and take a look, and well, this seems to be appearing a lot of times where we have this common side here, so we know that that's going to be congruent to itself. So let's go ahead and use that as part of our proof as well. We see that that's going to be one of the sides in our included angle, hopefully, and then hopefully we'll be able to show that MD is congruent to MB. But let's go ahead and let's write out that next statement, that MY is going to be congruent to MY. And that is our reflexive property. So then again, we have a side, we have an angle. We want to be able to show that MD is congruent to MB. So we have to try and see if there's any information we're given that would allow us to say that those are congruent to each other. So the only other information that's given to us is that those 3 segments pass through the center of the circle. Also, I don't really see anything else in our diagram that might help us here. So if we know that these segments are all passing through the center of the circle, if you go back to your definition of a circle, and if you think about what it meant for something to be the center of the circle, we know that if M is the center of our circle, that all points along the circumference of that circle are going to be equidistant from point M. So knowing that, if we know that this is the center, and we know that D is a point on the circumference of our circle, and B is a point on the circumference of our circle, we know that those 2 segments are then going to have to be congruent to each other. Again, because they are going to be the same distance away from that center. You can think about them both as being radii of our circle, and we know that any 2 radii have to be congruent to each other. Half the diameter, we know that that's going to have to be equal to the same half of the diameter on that side. So here we know that MD is going to be congruent to MB. And really our justification here, we're just kind of using what we know about the center of our circle. So I'm just going to go ahead and justify that as the definition of the center of a circle. So to this point, we've shown that angle 3 and angle 4 are congruent. We have shown that 2 adjacent sides around that included angle are congruent to each other. So our last step here, we can then jump to the conclusion that triangle DMY is congruent to triangle BMY. And that is once again because of our side angle side congruence theorem. All right, the next theorem is theorem 4.5, which is the hypotenuse leg congruence theorem. This says that if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of the second triangle, then the 2 triangles are congruent. So this theorem is specific to right triangles. And again, what we're saying is that if the hypotenuse, which remember is opposite our right angle, if we know that those are congruent to each other, and that one of our legs is congruent to its corresponding side in the other triangle, then those 2 triangles must be congruent. We don't have to show that the included angle is congruent. We don't have to show that the other side or the other leg is also congruent. If we just can show that the hypotenuse and one of our legs is congruent to the corresponding hypotenuse and leg, then we can say that the 2 triangles are congruent. So let's take a look ahead and look at this proof here. So I've broken it down a little bit different than it is on your page. I put it side by side since I needed some more space and it worked better to put it horizontally. But we're going to go ahead and take a look. We have quite a few givens here. We're given that AC is congruent to EC. We're given that AB is perpendicular to BD. Given that ED is also perpendicular to BD. And we're given that AC is a bisector of BD. We want to prove that the two triangles ABC and EDC are congruent. So let's kind of take a look again at these givens. We have quite a few here, so let's take a little bit more time to kind of look at them and see what that's telling us in our diagram. So we are given that AC is congruent to EC. You can see that that is already labeled in our diagram, that those two sides are congruent. We know that AB is perpendicular to BD. So if AB is perpendicular to BD, we know that that must be a right angle. If ED is perpendicular to BD, we know that that must be a right angle. And we know that AC is a bisector of BD. So if we have AC being a bisector of BD, well, segment bisector means that it's going to split our segment into two congruent segments. So we know that this would have to be congruent to this. So if we take a look at those givens, that's going to give us a lot of information and really help us get off to a great start for our proof. So let's go ahead and let's come over here and start kind of working through some of these statements and reasons that we need to fill in. First thing, we're given that AC is congruent to EC. That was one of our givens. We're then saying that AB is perpendicular to BD and ED is perpendicular to BD. That was another one of our givens as well, or two of our other givens. Next statement is that angle B and angle D are something. And you can see over here, our justification is that it's the definition of perpendicular lines. So if we know that the lines are perpendicular, we know based on the definition that that would have to form right angles. So we know that angle B and angle D are right angles. Next statement is that triangle ABC and triangle EDC are blank, and that's the definition of a blank. So we have to try to think about what we're using here. So we said that they were congruent. We said that lines are perpendicular. We said that those are right angles. So next logical step, if we know that they're right angles, what would that tell us about the triangles? Well, if these are right angles, that would tell us that these triangles have to be right triangles. And that is the definition of a right triangle. So you might be wondering why that's important to say. Well, remember, our goal is to use the hypotenuse-leg theorem based on what we kind of set up here. And in order for us to use that theorem, we have to be able to say that the two triangles we're referring to are right triangles. That was kind of one of the original stipulations we had to have. So we have to include somewhere in our proof that we have right triangles. All right, so let's go ahead and take a look. Next, moving on down, we see that AC is a bisector of BD. So that was our last given. And we know that BC is congruent to DC, we talked about, because if AC is a segment bisector, we know it's going to divide it into two congruent segments. Lastly then, we're saying that triangle ABC is congruent to triangle EDC. So if we look at this, when we looked at all that information that we had a right angle here, we had this side being congruent, we had this side being congruent. When we look at our diagram, we see that this side is opposite our right angle, so that is the hypotenuse, which is congruent to the corresponding hypotenuse. We also see that one of our legs, which is adjacent to our right angle, is congruent to its corresponding leg over here. So we know that based on the hypotenuse leg theorem, that those two triangles must be congruent. Our last example here, example 4, more of a real-world type problem, something that you might actually encounter in your real life. We see that the entrance to a ranch has a rectangular gate as shown in the diagram. You know that triangle AFC is congruent to triangle EFC. So we know that triangle AFC is congruent to triangle EFC. What postulate or theorem can you use to conclude that triangle ABC is congruent to triangle EDC? So now we're referencing triangle ABC and triangle EDC. And as you can see, we of course want to go ahead and write a proof for this in addition to finding out what postulate or theorem that we can use. So some things to remember in a rectangle, remember that all the angles are 90 degrees and that the opposite sides are congruent. So when we look at our diagram, when we look at these two triangles specifically that we're trying to show are congruent, let's see if any of this information will help us. So when we look at that, when we look at these two triangles, first thing that I see is I know that these two angles here have to be right angles, since again, all angles in a rectangle are going to be right angles. Next thing I notice is that opposite sides here, so the left side and the right side, we're going to know that those are going to have to be congruent because opposite sides of a rectangle are congruent. At this point, we can't say anything about these sides because based on the fact that it's a rectangle and the given information, we can't immediately say that those are going to be equal to each other. We don't necessarily know that C is the midpoint. So based on our information that we've kind of developed here, let's go ahead and just start this proof, and then we'll try to figure out some other information that would allow us to complete the proof. So first thing that we said was that angle B and angle D are right angles. And that's really based on the fact that all angles in a rectangle are right angles. You can almost think of that as a given, or it's just a characteristic of a rectangle. We really don't have any theorem or postulate to prove that. Second thing that we then said was that AB, and actually let me back up a second. So if we know that those are right angles, remember a proof we did earlier with those right angles, we then said that they were right triangles. If we think about this, we said earlier we weren't able to say anything about these two sides, but if we could show that the hypotenuses were congruent, we would then be able to use our hypotenuse leg theorem. So we probably want to make sure that we say that we know that these two triangles are right triangles based on the fact that they have a right angle. It may come in handy later when we go to prove that they are congruent. So we're going to say that triangle ABC and triangle EDC are right triangles. And that is the definition of a right triangle. All right, so let's come back to the other statement that we had figured out, that AB is going to be congruent to ED. And really, that's just because we know that opposite sides of a rectangle are going to be congruent. All right, so like I said, we're going to need to figure out some more information to be able to complete this proof. So let's go back to that given that triangle AFC was congruent to triangle EFC. If we know that triangle AFC is congruent to triangle EFC, well, let's use that as our given. So if we know those two triangles are congruent, remember that congruent triangles always have all corresponding angles and all corresponding sides being congruent. So because these two triangles are congruent, we know that AC must be equal to EC because those are both corresponding sides of those congruent triangles. So we're going to go ahead and say that AC is congruent to EC. And the reasoning we're going to give for that is shorthand what we call CPCTC. I'm going to go ahead and write out what that actually stands for. So CPCTC stands for corresponding parts of congruent triangles are congruent. So basically this allows us to say that if we know that these two triangles are congruent, that all of the corresponding parts must also be congruent. So since these two triangles are congruent, we're then allowed to say that AC has to be congruent to EC. So now when we look at our diagram, we have shown that there are right triangles based on the right angles with B and D. We have now shown that the hypotenuse, the side opposite the right angle, is congruent. And we know that one of our legs must be congruent. So we now have enough information to say that triangle ABC is congruent to triangle EDC. And that is because of our hypotenuse leg theorem. All right, that's it for our notes today. Thank you, and please let me know if you have any questions.